This is new this year, it's not in our textbook. And the standards are that I can write a system of inequalities. That's what we did today, right? Writing a system of inequalities. But we're going to have some constraints on our problems, right? So the key thing is we're going to look at constraints. I'm going to graph it on a coordinate plane. I'm going to use a linear system to minimize and maximize. So keywords that we are looking at there. We are looking at minimizing or maximizing my desired solution. And we want to be able to interpret it in the context of the situation. If you would please read, Whitney, where it says we have.
We have spent a lot of time learning about linear systems or comparing inequalities. Today we're going to talk about how to use systems to find maximum or minimum values of some quantity given certain constraints. For example, in problem below, we want to find out what to buy so that we maximize the number of healthy tomatoes that I can grow using $40 an hour. We're not going to solve this one.
All right, so we're not going to solve this one right now. Ben, would you please read what it says?
In the box?
Yep.
Okay. You want to spend no more than $40 at most, or at most 15 plants. You want to maximize the pounds of tomatoes you'll get. How many of each plant should you buy? Justify your answer.
So when we are looking at this, we're thinking that the Romas are $2 and the cherry tomato are $3. Could you write an equation that says you want to spend no more than 15 plants, right? We're thinking about our two systems, different ways of writing our systems. At this point, we would have one with the number of tomato plants, right, and one with the value. You've done this, right? We've been writing these equations. So, vocabulary at the top of the next page. Josie, or that next page down. Josie, you want to read for us the vocab? Valerie, keep going.
Constraints in the situation of one system of inequalities. The graph of the system is called the feasible region. This region contains all the points that satisfy all the constraints, all of the possible answers. We, however, are not looking for all the answers, we're just looking for one.
Sanjay, keep going.
The quantity that we're trying to maximize or minimize is modeled with an equation called the objective function. Often this quantity is about the cost or profit.
Keep going.
If there is a maximum or minimum value of the object function, it will occur at one or more of the vertices of the feasible region. Use the coordinates of the vertices in the equation for the object function to see which solution is the biggest or smallest to find the maximum or minimum.
So what we're going to be doing is we're going to be graphing, and you might have 3 different equations, and this one actually has 5. They only show 3 of them. You see the red line, you see the green line, and you see this gold line, right? What you don't see is that we can't have it be what kind of a number? It can't be negative. So they don't have those ones, but it can't be negative. So when we look at this, we're looking at where are my points of intersection. So I'm going to look for this point of intersection. This one actually has 4 points that I would want to check for optimizing, okay? For my objective function and to optimize my solution. I don't want to care about all of these solutions that we did yesterday when I said give me possible solutions, right? And we could give numbers way down here, like I had someone in the other class say negative 100 and something and a negative 20, right? Because that would be a solution if it was just all these systems that overlap, because it'd be way over here and way down here. That would be a solution. We want to be talking more about optimizing it. So when we set up our problems like this, it's often helpful to make a table where we have our constraints, we have our variables, and we have our total, okay? You're going to put the variables along the top, the constraints and the objective function on the side, and we're going to fill in what we know as we look at it. So a lot of times you're going to see this. If you go to linear programming on Khan Academy, or if you do a Google search of it, you're going to see some stuff like this. So it's all about maximizing our profit a lot of times. So if you were going to continue reading, Brecken, would you read please where it says you're going?
You are going to sell t-shirts and sweatshirts at a blues festival. You are working with the following constraints. You have at most 20 hours to make the shirts. You can spend no more than $600 on supplies. You want to have at least 50 items to sell. Time and cost information is in the picture. How many t-shirts and sweatshirts should you make in order to maximize your profit? What is that maximized profit?
So here we have our t-shirts, we have our sweatshirts are going to be Y, and we're going to have our total. So the first thing we want to take a look at is it says it takes 10 minutes to make the supplies. It costs $4, $6 profit on the blue shirt, right? On our red shirt, 3-color sweatshirt that we're looking at, it takes us 30 minutes to make. Supplies cost 20 and profit is 20. So first thing we want to look at is how much time do we have. So we had 20 hours. Notice this was talking about time in minutes. So we had to convert 20 hours, right? 20 hours, we have to change it to, our total here was in minutes. We wanted this number to be in minutes so that it went along with the 10, so we didn't have to use a fraction, right? 10 minutes out of an hour would be 1/6, kind of an ugly fraction, right? So we're going to change all of our hours to minutes. Does that make sense to everyone, how we get to 1200, okay? And then each one, 10x plus 30y, that's how much time. We want to, it says, we want to sell at least 50. So x and y together are 50. But it's actually going to be, we want to sell more than 50, right? So x plus y, we want to sell at least 50, so that's going to be the equation, right? So this is just kind of putting our information in, then you put the equations over here, right? The next one, it tells us if we are looking at that, that when we are looking at it, that we're looking at the, like our cost, right? That's our expenses. $4 to make the blue one, to make the t-shirt, 20 for the other one. And if we are looking at it, we want to spend no more than 600. So no more than 600 means we want it to be less or equal. Then again, you can't have negative numbers. So x and y, t-shirts and sweatshirts both have to be greater or equal to 0. So what you're going to be doing today and tomorrow, I might give you today these equations and ask you, and I might give you tonight in your homework, I might ask you to look at this, so next week, Monday. I might ask you to look at this and which one is going to be our, how are we going to maximize it? So, this objective function, that's my profit. That's what we are looking at. 6x plus 20y. We want to find when will we make the most money. We don't know what that profit is yet because it depends on my points. So, what you're going to do is you would graph all 5 of the equations. Okay? Here's the greater, when y is greater than 0, here's where x is greater than 0, we would have shaded. We're going to have this equation where we have x plus y is less or equal to 50. That's going to be this one, right? We're up here at 50, and you can't see the 50 up here, right? So 50 and 50 are my x and y intercept. 4x plus this one where it's less or equal to 600, that's going to be this one, if you looked at the points that we're looking at. And then we have our, so you're going to graph each equation. So it says then find the coordinates involving the 2 equations where they intersect. So this point right here at B, if we are looking at, let's change our color, right here. This point, if we are looking at it, is located at, if we are looking at that point, looks like what? 20. So let's look at the first one they have. They have over here, they have 50, 0, right? This is point A. Okay. Point B up here is at 25, 25. So it's less than 30, right? It's less than this 30. Right? So here's 30 right here. This is 25, 25. That's point B. Okay. Point C is over here. And again, that's why the scale that some of you going by 2s, it's really hard to tell that this is 75, right? A little easier to see the 15. But just by setting your scale big enough, so you're going to definitely want to make sure you do that. And here we have, this last point is down here, point D is our 120. Okay? So what you're going to do is you're going to substitute in these 4 points into your objective function. So 6 times 50 plus 20 times 0, $300. Which one looks like, if you're looking at their work that they did, Which one looks like we're going to maximize our profit with which point? With point C, right? Point C maximizes it. It gives me the most profit if I am looking at that. So when you look at your equations, it's going to be really important that you show me this work in substituting this in. So for our solution, what we are going to write, just like when you answer those story problems from D6 and D5, selling 75, so again, writing this down right here in your notes. Do you not have your notes in? Okay, go back there and grab one so you can write it in there. So selling 75 shirts and 15 sweatshirts will maximize our profit. And then you want to tell what that maximized profit is, which is $7.50. Okay? So make sure you have this written down. That next one going down. So what we're going to do is next week, when you take a look at what we are going to be doing with our assignment. So next week we're going to have 8B in the workbook. Then you're going to have this linear programming assessment. You'll also have the review 9. We're going to start that new linear systems, and on your test day, this linear programming will be due at the end of the hour. Most people, from what I've talked to my other colleagues, it's taken most people 20 to 30 minutes, and you turn it in at the end of the class period. Did everyone get this written down? Mm-hmm. And then our test is going to be the end of next week. Okay? So, if we are reading in this one, Emily, you want to read first?
Toys to go makes toys at plant A and plant B. Plant A needs to make a minimum of 1,000 toy dump trucks and fire engines. Plant B needs to make a minimum of 800 toy dump trucks and fire engines. Plant A can make 10 toy dump trucks and 5 toy fire engines per hour. Plant B can produce 5 toy dump trucks and 15 toy fire engines per hour. It costs $30 per hour to produce toy dump trucks and $35 per hour to produce toy fire engines.
So there's lots of information as we look at it. So plant A, minimum of 1,000. So plant A combined has to be what? 1,000. How many, if we are looking at that, how many toy dump trucks do we know plant A can make? So we got 10x, right? And how many fire engines? 5. This is just filling in our boxes. We don't have any inequalities, right? We're just filling this in. So plan B makes, if we are looking at it, has 5 toy dump trucks, right? And it has 15. And our amount here was 800. And now we're trying to make our profits, right? What do we know? Or if we are looking at $30 an hour to produce our toy dump truck, right? 35 to make our toy fire engines. So we are going to have this equation being something like 30, right, x, and what would you think? 35y. And the combined is the 30x plus 35y. That's our, this is really our objective function, right? That's how much money. And we're trying to make the minimum here. So if we are looking at our constraints, I found when I was trying to write this in this little box, it gets a little crowded. I'm going to show, so I'm not going to write it in pen because my pen when I write up here gets a little sloppy. So we agree that it has to be greater or equal, right, than both D and F. Now they use D and F instead of X and Y. I prefer, if you're looking at this, probably your X and your Y, right? X and Y, X and Y. So we keep it the same as up here. Our objective function is that last one, right? Cost equals 30, and again, if you want to put 30x plus 35y. So we want to look at 3 points that we have for solutions. So they graph these two systems. This first point is up here at 0, 200. The second one is at 88, 24. And the third one is at 160, 0. So this is very much like when we did the other day that perimeter problem in our notes, right? If you're making the backyard for your dog, you want to try to give it the maximum amount of space, right? Instead of having it be really small, unless you have a really small dog. So what do we do at this point? We're going to find our cost. Everybody do you think? I'm going to put C equals what? 30. Wait, what is my X here? So I'm going to go to this equation, right? So I have C equals 30 times
X.
What is my X?
The dump truck.
Yes, and in this solution right up here that I think I have how many? 0. So I'm going to take 30 times 0 on my calculator, plus, which is 0, times, or plus, 35 times what? 200. Put that in your calculator. Our first cost comes out to be 10,000? 7,000. Now we're going to go to the second one. C equals. And now we are going to plug in. So if you're helping me do this one, Micah, I'm going to put down what first? 30 times? 30 times 88. Micah, keep going.
Plus 35 times 24.
So on your calculator, you're going to do some multiplying, right? 30 times 88 plus 35 times 24. 3,480. Thank you. To get the last one, I'm going to take 30 times 160. And then that's going to be 35 times 0, so that's going to be a plus 0, right? 4,000. What'd you get?
4,800.
Are we trying to maximize or minimize our costs? Minimize. So we definitely don't want to choose this one. And here, if we are looking at this. So we would want to answer the question with, we want to do, if we are looking at this, and I know yours probably is a little kind of full with just that work. We are going to maximize, so we are going to say 88 hours, right, on the dump truck. And we are looking at 24 hours on fire engine. For a minimum, and so we were looking at this, a minimum cost of $3,480. Okay, is it like what we've been doing? Sort of. It just goes, once we find those intersection points of our equations, we are just trying to find out which one is either the minimum or the maximum that you're going to be looking at. Okay? So, this is what your homework will look like. I give you pretty nice numbers. Okay? So on D8A, there are 3 questions. Okay? 3 questions. It says, in the problem, you're given the constraints of an objective function. Graph the constraints, then use the objective function to maximize. Okay?